welcome to my YouTube channel. I'm Professor Charles, and today we're diving into the fascinating world of mathematical logic. In this video, we'll explore the fundamental concepts of variables, statements, and quantifiers, unraveling the intricate connections that lie at the heart of mathematical reasoning.
In the fascinating realm of discrete mathematics, we encounter a set of powerful concepts that serve as the building blocks of logical reasoning and proof. So let's delve into some of these fundamental ideas: propositions, predicates, and quantified statements. Propositions are basic statements that can be evaluated as either true or false. They form the foundation of logical reasoning. For example, consider a proposition: the sum of two even integers is always even. This statement can be assessed and proven to be true or false. Moving on, we have predicates. Predicates are statements that involve variables and become propositions when we substitute specific values for these variables. They express properties or relationships that can vary based on the input. For instance, we can have the predicate P of x that states x is divisible by 3, or a predicate Q of x and y that expresses x is greater than y. These predicates become propositions when we assign actual values to the variables. Lastly, let's explore quantified statements. These statements involve the use of quantifiers, which are words like for all and there exists. Quantified statements allow us to make generalizations or claims about the properties of elements within a set. For example, the statement for all x, P of x, every integer is indivisible by 1 asserts that every integer satisfies the property of being divisible by 1. On the other hand, the statement there exists an x such that Q of x, there exists an integer that is greater than 10, claims that at least one integer satisfies the property of being greater than 10. By employing these concepts of propositions, predicates, and quantified statements, mathematicians can delve into the intricacies of discrete mathematics, constructing logical arguments and uncovering hidden truths within various mathematical structures. When it comes to evaluating mathematical statements, we need to determine their truth values by applying logical rules, considering mathematical properties, and examining specific cases. There are several tools and techniques available for evaluating mathematical statements. Truth tables, for instance, provide a systematic way to determine the truth values of complex propositions based on the truth values of their component propositions. Logical equivalences help us identify equivalent statements, allowing us to simplify and reason about expressions. Additionally, proof methods like direct proof and proof by contradiction enable us to establish the truth of statements through logical reasoning. Counterexamples, on the other hand, can be used to demonstrate the falsity of a statement by providing a specific case that contradicts it. In the realm of discrete mathematics, formal systems such as propositional logic and predicate logic provide a rigorous framework to analyze and manipulate mathematical statements. These formal systems allow us to define precise rules of inference and syntax for constructing valid arguments and proofs. The correct evaluation of mathematical statements is essential in constructing valid arguments, proving theorems, and solving problems across various areas of discrete mathematics, including logic, set theory, graph theory, and combinatorics. It ensures the soundness of our mathematical reasoning and provides a solid foundation for advancing our understanding of these disciplines. In the realm of discrete mathematics, statements can be classified into two categories: atomic statements and molecular statements. Let's delve into these types and explore their characteristics. Atomic statements are foundational statements that cannot be divided into smaller statements. They represent indivisible units of information or assertions. For instance, consider the atomic statements: the sum of two even numbers is always even. There exists an element x in the set S such that P of x holds. Molecular statements, on the other hand, are formed by combining atomic statements or other molecular statements using logical connectives or quantifiers. These statements allow us to express more complex relationships, properties, or implications. For example, let's look at some molecular statements. If a number is divisible by 6, then it is divisible by both 2 and 3. This molecular statement combines the atomic statements regarding divisibility to establish a relationship between them. For every positive integer n, there exists a positive integer m such that m is greater than n. This molecular statement utilizes quantifiers to express a generalization about the existence of a positive integer m that is greater than any given positive integer n. By distinguishing between atomic and molecular statements, we gain insights into the structure, relationships, and implications of mathematical statements. This classification aids us in analyzing and reasoning about these statements within the realm of discrete mathematics, enabling us to construct intricate arguments, explore various mathematical properties, and tackle challenging problems. Logical connectives play a crucial role in forming molecular statements by connecting atomic statements. Let's explore some commonly used logical connectives. Conjunction AND. The conjunction connective combines two statements and requires both to be true for the compound statement to be true. For example, consider the statement, the number is even and greater than 10. Both conditions must hold simultaneously for the compound statement to be true. Disjunction OR. The disjunction connective combines two statements and requires at least one of them to be true for the compound statement to be true. For instance, consider the statement, the shape is either a circle or a square. If the shape satisfies either condition, the statement is considered true. Implication if-then. The implication connective establishes a conditional relationship between two statements where the truth of the first statement implies the truth of the second statement. For example, the statement, if it rains, then the ground will be wet, expresses a conditional relationship between rainfall and wet ground. If it rains, it implies that the statement or that the ground will be wet. Negation not. The negation connective negates the true value of a statement, flipping it from true to false or vice versa. For instance, the statement, it is not the case that the number is prime, negates the true value of the original statement about primality. By utilizing these logical connectives, we can build molecular statements that capture more complex relationships and conditions between two statements. Understanding and employing these connectives is crucial in constructing precise mathematical statements and reasoning about them within the realm of discrete mathematics. An implication or conditional is a molecular statement of the form P to Q, where P and Q are statements. We can break down the implication into hypothesis or antecedent P, conclusion or consequent Q. An implication is considered true as long as either P is false or Q is true or both. It is only false when P is true and Q is false. The hypothesis represented by P sets a condition or assumption for the implication. It is a statement that we consider to be true or false. The conclusion represented by Q is a statement that follows from the hypothesis. It is a result or consequence that we expect or evaluate based on the true value of the hypothesis. To evaluate the true value of an implication, we consider all possible combinations of true values for P and Q. If the hypothesis is false or the conclusion is true or both, the implication is considered true. However, if the hypothesis is true and the conclusion is false, the implication is false. Understanding the structure and evaluation of implications is essential for logical reasoning and constructing valid arguments within the realm of discrete mathematics. In the exciting world of mathematics, implications play a significant role and appear in various contexts. Let's dive into an example that involves divisibility to understand how implications are used. Considering the following implication, if a number is divisible by 6, then it is divisible by both 2 and 3. In this statement, we have a hypothesis or antecedent, a number is divisible by 6. This sets a condition or assumption of an implication. We are considering numbers that are divisible by 6. The conclusion or consequent of the implication is, it is divisible by both 2 and 3. This represents the result or consequence that we expect or evaluate based on the true value of the hypothesis. To understand the implication, we evaluate different scenarios. If a number satisfies the hypothesis and divisible by 6, it implies that it is also divisible by both 2 and 3. This is because 6 can be factored into 2 and 3. So any number divisible by 6 will also have factors of 2 and 3, making it divisible by both. Implications like these are widely used in mathematics to establish relationships, make predictions, and draw conclusions based on given conditions. They help us reason logically and build rigorous mathematical arguments. By exploring this example, we can see the power and significance of implications in mathematics, providing a foundation for understanding and applying concepts of divisibility and beyond. In the captivating realm of implications, it is crucial to keep in mind that there are statements and hold a specific truth value. Let's delve into the intricacies of determining the true value of an implication and understand their behavior. The true value of an implication is contingent upon the true values of its hypothesis and conclusion. We evaluate these components to establish their overall true value of the implication. When it comes to the true value of an implication, it is true in a couple of scenarios. First, if the hypothesis is false, irrespective of the true value of the conclusion, the implication is considered true. This is because when an initial condition or assumption is not met, the implication does not make any specific claim or restriction. Additionally, if the conclusion is true, regardless of the true value of the hypothesis, the implication is also considered true. This signifies that the truth of the conclusion supports or follows from the hypothesis, even if the initial condition is not satisfied. However, an implication is false in one specific case. If the hypothesis is true and the conclusion is false, the implication is false. This occurs when the expected result or consequence contradicts the initial assumption, indicating that the relationship proposed by the implication does not hold. Understanding the behavior and truth evaluation of implications is of utmost importance in mathematics and reasoning. It allows us to establish the validity of statements, draw logical conclusions, and construct robust arguments. By keeping these principles in mind, we can navigate the world of implications with confidence and accuracy, ensuring that our mathematical reasoning is sound and well-founded. When it comes to proving the implication denoted as P implies Q, an effective strategy is to assume the truth of the hypothesis P and then deduce the truth of the conclusion Q. This approach is known as a direct proof, and it offers a powerful method to establish the validity of implications. To prove P implies Q, we begin by assuming that the hypothesis P is true. By making this assumption, we establish a temporary condition or assumption that allows us to explore logical consequences. Next, our objective is to deduce or derive the truth of the conclusion Q based on the assumed truth of the hypothesis P. We employ logical reasoning, mathematical principles, and deductive techniques to establish a valid chain of arguments that leads us to the desired conclusion. If we successfully demonstrate that by assuming the truth of P, the conclusion Q logically follows, then we have proven the implication P implies Q. This means that whenever the hypothesis P is true, the conclusion Q must also be true, supporting the validity of the implication. The strategy of assuming the truth of the hypothesis and deducing the truth of the conclusion is a fundamental approach in mathematical proofs. It enables us to construct rigorous arguments, provide evidence for the validity of implications, and establish the logical relationships between statements. By employing this strategy, mathematicians can strengthen their proof techniques, explore the connections between mathematical statements, and contribute to the development and understanding of mathematical concepts and theorems. The converse of an implication P implies Q is the implication Q implies P. However, the converse is not logically equivalent to original implication. That is, whether the converse of an implication is true is independent of the truth of the original implication. Additionally, the contrapositive of an implication P implies Q is the implication negation of Q implies negation of P. When we consider an implication of the form P implies Q, the converse of this implication is formed by switching the positions of P and Q, resulting in Q implies P. It explores the relationship between the conclusion and hypothesis in the original implication. However, it is important to note that the converse is not logically equivalent to the original implication. This means that the truth or falsity of the converse does not necessarily indicate the truth or falsity of the original implication. They are distinct implications and may have different truth values depending on the specific conditions. Furthermore, in addition to converse, we have another related implication known as the contrapositive. The contrapositive of an implication P implies Q is formed by negating both the hypothesis and the conclusion. This results in the implication negation of Q implies negation of P. The contrapositive allows us to establish equivalent implication to original implication. The contrapositive is true, and the original implication must also be true, and vice versa. The logical equivalence holds between an implication and its contrapositive. Understanding the differences between the converse and the contrapositive of an implication is crucial in logical reasoning and mathematical analysis. It reminds us to consider each implication separately and evaluate their true values independently of each other and the other original implication. By recognizing the independent nature of the converse and the logical equivalence of the contrapositive, mathematicians can effectively reason and establish the validity of implications, ensuring the accuracy and rigor of their logical deductions and arguments. In the vast realm of mathematics, we come across numerous examples where the converse of a true implication can be false or true. Let's explore these scenarios and understand the dynamics of converse applications. Consider the implication: if a number is greater than 2, then it is prime. This statement holds true and asserts that any number greater than 2 must be prime. However, when we examine the converse, if a number is prime, then it is greater than 2, we find that it is false. This means that there exists prime numbers that are greater than 2. The converse does not hold true in this case. On the other hand, there are instances where the converse of a true implication is also true. For example, let's consider the Pythagorean theorem. The original implication states that if a triangle has sides a, b, and c satisfying the equation a squared plus b squared equals c squared, then it is a right triangle. This implication is true and widely known. Interestingly, the converse of this implication also holds true. If a triangle has sides a, b, and c satisfying a squared plus b squared equals c squared, then it is a right triangle. In this case, the original implication and its converse are both true. These examples highlight the diverse nature of converse implications in mathematics. While there are instances where the converse of a true implication is false, there are also cases where the converse is true, aligning with the original implication. Understanding and analyzing the converse implications allow mathematicians to navigate the intricacies of logical reasoning and mathematical arguments. By evaluating the truth or falsity of the converse, we gain insights into the relationships between statements, and we can assess the conditions under which implications hold or do not hold. By examining various examples and scenarios, mathematicians continually expand their understanding of converse implications, contributing to the development and exploration of mathematical concepts and theorems. An if and only if statement represented as P if only and only if Q, or P is true if and only if Q is true, signifies that the truth of P is dependent on the truth of Q and vice versa. It combines both an implication and its converse to establish a bidirectional relationship between Q and P. For example, let's consider the statement: an integer n is even if and only if n squared is even. This can be expressed by two implications. The implication if n is even and n squared is even, P implies Q, asserts that if the hypothesis P, which states that n is even, is true, the conclusion Q, which states that n squared is even, must also be true. The converse implication, if n squared is even and n is even, Q implies P. It states that if the hypothesis Q, which asserts that n squared is even, is true, the conclusion P, which states that n is even, must also be true. By combining these implications, we establish a bidirectional relationship between P and Q, meaning that P is true if and only if Q is true. If P is true, then Q must also be true, and if Q is true, then P also must be true. The if and only if structure provides a powerful tool for expressing precise relationships, conditions, and properties in mathematics. It allows mathematicians to analyze and reason about concepts in clarity, ensuring a solid foundation for logical deductions and mathematical proofs. In mathematical sentences, we often encounter predicates and quantifiers, which are essential for expressing statements about variables. Predicates are expressions that contain variables and are used to describe properties or relationships. These variables represent elements from a set, and the predicates assign properties or conditions to those elements. For example, we may have a predicate like P of x is divisible by 3, where x represents integers and the predicate asserts the divisibility x by 3. Quantifiers also allow us to make statements about these variables and express generalizations or existence claims. There are two primary quantifiers used in mathematics: the universal quantifier. The symbol universal quantifier is used for all or every. It asserts that a statement holds true for every element in a given set. For instance, when we say for every x P of x, it means that the predicate P of x is true for every x in the set under consideration. This quantifier emphasizes that the property described by the predicate applies to every element. The existential quantifier, the symbol is read as there exists. It indicates the existence of at least one element in a set for which a statement is true. For example, when we say there exists an x such as P of x, it means that there is at least one x in this set for which the predicate P of x is true. The quantifier highlights the existence of elements satisfying the condition described by the predicate. By utilizing these quantifiers, mathematicians can make precise elements about variables and express notions of generality or existence within mathematical contexts. These quantifiers are vital for formalizing mathematical reasoning, making claims about elements of sets, and enabling rigorous proofs and deductions. The negation of the universal quantifier is expressed as not every element satisfies the property P. This is equivalent to the statement which states that there exists at least one element that does not satisfy P. In other words, when we negate the universal quantifier, we shift the focus from all elements satisfying the property to the existence of at least one element that fails to satisfy it. Similarly, the negation of the existential quantifier is expressed as there does not exist any element satisfying the property P. This is equivalent to the statement which states that every element does not satisfy P. When we negate the existential quantifier, we emphasize that there is no element that meets a given property. By understanding the negation of the universal and existential quantifiers, we gain insights into the logical relationship between statements and the interplay between universality existence. These negations allow us to reason about the absence of properties across all elements and the presence of properties that fail to hold for at least one element in the set. In mathematical discourse, precision plays a vital role. However, there are situations where we can relax certain conventions while maintaining a shared understanding. One such convention involves the assumption that sentences containing predicates with three variables are intended as statements, where the variables are universally quantified. Let's consider an example to illustrate this convention. Suppose we have the statement, if a shape is a shape, then it is a rectangle. Technically speaking, this sentence is not a statement as it contains two predicates, is a square, and is a rectangle. In formal logic, we typically require variables to be explicitly quantified. However, in mathematical discussions, we can interpret this sentence as applying the convention of assuming universal quantification. We understand it as the statement for all shapes, if it is a square, then it is a rectangle. Although the variables are not explicitly quantified, we assume that the statement applies universally to all shapes, implicitly quantifying the variables. By adopting this convention, we can effectively communicate mathematical ideas and statements even when the formal logical notation is not explicitly used. It allows for a shared understanding among mathematicians, enabling the exchange of information and reasoning. While precision remains crucial in mathematical discourse, recognizing and employing conventions like this allows for flexibility in communication as long as there is a clear and mutual understanding of the intended meaning behind the expressions and statements being used. Now, in discussions involving predicates and statements, it is not uncommon to use imprecise language. For example, we might write something like, let P of n be the statement n is prime. However, technically speaking, this is an incorrect use of terminology. The more accurate way to express this would be to say, let P of n be the predicate that evaluates to true when n is prime. By defining P of n as a predicate, we acknowledge that it is a function that takes an input, in this case n, and produces a statement. In other words, for each value of n, P of n represents the statement n is prime. Being mindful of the distinction between predicates and statements allows us to maintain clarity and precision in mathematical discussions. Predicates describe properties or relationships that can vary based on the input values, while statements are concrete expressions that can be evaluated as either true or false. By using precise language and understanding the difference between predicates and statements, we ensure accurate communication and a clear understanding of the concepts at hand.